Hello, hello, it is Mrs. Edwards and we are back. It is time to do math and I love it. We're going to be doing some logarithmic differentiation today, which is quite a mouthful. And the real question when you're going to be using this type of differentiation is when is it that you should take the log of both sides before you take the derivative? The answer is twofold. There are two scenarios when you should do this. Scenario number one, if you see a variable in the base and a variable in the exponent, we need to take the log of both sides of the equation before we try to take the derivative. The reason that that happens is we know how to take the derivative of things that have a variable base, like x to the third power is 3x squared. We also know how to find the derivative when there is just a variable up in the exponent spot. For example, 2 to the power of x's derivative is 2 to the power of x multiplied by the ln of 2. But we do not know how to find the derivative when both the base has a variable and the exponent has a variable. And logarithms allow us to move the exponent and get it out of that exponent spot, which is going to solve that issue for us. Okay, and then the second scenario where you can take a log of both sides of the equation in front of you before you take the derivative is if the equation in front of you is just frankly hideous. You're like, oh my gosh, there's a fraction, there's a root in the fraction, there's some exponents, there's just a lot going on. Well, a logarithm, the beauty of logs, like why I love logs, is it allows you to pull apart with all those log properties something that is enormous and hideous into a bunch of little tiny easy problems. And in that second situation, I just want to say it is optional to take the log of both sides, but boy, does it make the calculus so much easier. Let's go ahead and start with the first scenario where we have a variable in the base and in the exponent. Okay, so we've got the derivative of x to the power of x. The giveaway here is we have an x as a base and we also have an x in the exponent spot. So immediately what I'm going to do is log both sides. Now when I say log both sides, I want to natural log both sides because the derivatives of natural logs are a lot easier than the derivatives of log, even base 10, but any base. So let's natural log both sides. Please be sure to write down in your notes every single time the equation you're working with has a variable in the base and a variable in the exponent, you need to immediately know to natural log both sides. Okay, using those powerful log properties, we can take the exponent, which is x in this case, and move it to the front. Okay, so that's exactly what I'm going to do. That x, I'm moving that to the front. So I have rewritten the original. I natural log both sides, lassoed that exponent to the front. I have not performed any calculus so far, but now that I have taken care of the variable base and variable exponent and turned it into just multiplication over here, we are ready to take the derivative. Keep in mind, we are finding the derivative with respect to x. So a couple of reminders, because you have implicit differentiation here. If you were finding the derivative of x squared, that'd be 2x. But if you were finding the derivative of y squared, that would be 2y, y prime. If you were finding the derivative of x to the fifth, it would be 5x to the fourth. The derivative of y to the fifth would be 5y to the fourth. The derivative of x would be just 1, while the derivative of y would be y prime. Derivative of 2y would be 2y prime, but the derivative of 2x is 2. All right, just a couple of reminders there, but let's take the derivative of the left-hand side. to find the derivative of a logarithm, you always want to know the base and you want to know the argument. Okay, so the base is e and the argument is y. And then the answer to a derivative of a log is a fraction. And with that fraction, you end up putting the natural log of the base in the bottom, the argument in the bottom, and the derivative of the argument in the numerator. That's just the rules for finding the derivative of a logarithm. Okay, then moving on there to the right-hand side, I'm taking the derivative of both sides, and we have x multiplied by the natural log of x. We'll need to use the product rule. So I have x times ln x prime plus ln x times x prime. Then let's go ahead and do a little bit of simplifying maybe. The ln of e is just equal to 1. Okay, so if that just equals 1, we'll have 1 times y, which is just over y. And then let's go ahead and take the derivative of the right-hand side. The derivative of ln x, again, the derivative of any logarithm is a fraction, and the denominator is the ln of the base times the argument, and in the numerator, the derivative of the argument. Okay, so here we go. There's the base e. So I'm going to have x. The ln of e is in the denominator, natural log of the base. The argument x is in the denominator, and the derivative of the argument in the numerator. And then way over here, the derivative of x is just 1. Okay, let's simplify a bit. What's the derivative of x? dy dx. The derivative of x is just 1. So I'm going to replace that with 1. Simplifying a little bit more, the natural log of e just equals 1. So that denominator is 1 times x. So I'm going to make that just x. Okay, then x multiplied by 1 over x is just 1, and ln x times 1 is just ln x. We want to find dy dx. That's equivalent to y prime, so I need to get y prime by itself, and to do that, I could just multiply both sides by y. I want to write my final answer to dy dx in terms of x. Okay, so that y right there, I don't want that y there. I want whatever y prime equals to be in terms of x. So I can look back up at the original. Right? The original y is equal to x to the x. So I'm going to replace that y with x to the x. So my answer, y prime, is equal to 1 plus ln of x multiplied by x to the power of x. And that is our final answer. Okay, in summary, one more time, the original equation, x to the power of x, we wanted to find the derivative. And because there's a variable in the base and a variable in the exponent, our first step was to take the natural log of both sides. The purpose of doing that is we can use the log properties to move the exponent and get any exponents out of the exponent spot and move that to the front. Sometimes you have to pull apart the log with addition and subtraction before you can move those exponents to the front, because a little reminder about that property of logarithms. The exponent must be on everything that you're taking the log of to move it to the front. If that exponent is not on everything, then you're going to have to pull it apart using another property before you move that exponent to the front. Okay, once you move it to the front, you're ready to take the derivative with respect to x, and at the end, get rid of the any y values with the original equation. So I'm saying one more. But boy, is this a doozy. In this problem, no matter how you approach this problem, the algebra is a little rough, not so much the calculus. But ultimately in this problem, the very first thing that crosses my mind as a calculus student, we do not like root form. We always, as soon as we see root form, we immediately change that to exponential form. So no matter what, that's my first step. Now, From here, if I wanted to take the derivative, I do not have an x that's in the base and in the exponent. So taking the natural log of both sides is optional. But the reason why we may want to do this is it allows us to pull apart this ugly mess. I would say all of that right there, kind of hideous. So if that's hideous, we can break it apart into some easier pieces. So I'm going to natural log both sides. The first thing we're going to do is start pulling apart, expanding the logarithm there on the right. I'm going to move that 1/3 to the front. Okay, next I have the natural log of division, and we can pull apart division with 2 logarithms of subtraction. Okay, so I'm going to keep pulling that apart. Okay, I have the natural log of the numerator minus the natural log of the denominator, still with 1/3 out front. I'm going to go ahead and multiply the 1/3 through. So if I multiply that 1/3 through, okay, I'm going to end up with this. And we have not performed any calculus so far. All we did was see a big ugly mess and decide that I don't want to take the derivative of that big ugly input function. So instead, I natural log both sides, use the log properties to pull this apart. Okay, now the calculus, we want to take the derivative of both sides with respect to x, and the derivative of ln y, the derivative of logarithms or fractions. You do the natural log of the base number, ln of e, but that equals 1, so I didn't put anything there. Y to the bottom and derivative of it in the top. Okay, there on the right-hand side, I'm going to do the same thing. 1/3 is my constant multiplier. I want to find the derivative of this logarithm. So x squared plus 1 goes in the denominator. The derivative of x squared plus 1 goes in the numerator. And that one extra step is ln of the base number, which in this case is e, goes in the denominator. That part really doesn't matter because the ln of e is equal to 1, so that's why we don't see it. Okay, continuing on there, minus 1/3 is a constant multiplier. The derivative of ln of x squared minus 1 is a fraction, and x squared minus 1 goes in the denominator. The derivative of x squared minus 1 in the numerator. And then the extra thing we always consider is that we also have the natural log of whatever the base is. And in this case, it's base e, but ln of e is equal to 1. So that's why we don't see that. If this was log base 2, then in the denominator, I would have had ln of 2. Okay, but ln of e is an identity, gets us back to 1. Whew, well, that's all the calculus. The calculus is done. We have found essentially y prime. Now I should get this by itself, okay, so I could do a little simplifying here. So let's multiply 1/3 times 2x over x squared plus 1 and 1/3 times 2x over x squared minus 1. Okay, and we're going to have that. Then to get the y prime by itself, I'm going to multiply both sides by y. And when I multiply both sides by y, I'm going to have y prime equals, and that y is over there. I want to also make sure that my final answer, right, dy dx is the same thing as y prime. I want it in terms of x, so I want to replace this y with the original. See how we can use the original equation to replace it? And when we replace it, now our answer is in terms of x. We have the answer to the derivative. It is in terms of x. No matter how you approach this problem, whether you logged both sides to break it apart to make the calculus easier, Either way, the simplifying, the full simplifying to get to the back of the book answer, whew, it is rough. Okay, so I'm actually going to take the time to review how to simplify this, your Algebra 2 pre-calc knowledge. All right, so let's start with what we have. And if you do decide to write this down, I would recommend watching it once so that you don't lose track of what's going on, and then just go back and copy it. All right, so I'm going to start by thinking, I don't like the cube root. I'm going to write that to the 1/3. Now, x squared plus 1 is to the first power, and x minus 1 is also to the first power. So you have a power to a power multiply. So the cube root of a fraction is the same thing as the cube root of the numerator over the cube root of the denominator. Okay, then I'm just going to, these take up a lot of space, so I'm going to replace what we had started with this guy right there. Okay, and really all I've done is say the whole thing to the power of 1/3 is the numerator to the 1/3 and the denominator to the 1/3. Okay, next thing I'm going to tackle is this first part, and I need to find a common denominator. Okay, both denominators already have a 3, but this first one needs an x squared minus 1, and this one needs an x squared plus 1. Okay, so I am simply look back and forth there. The only difference between the first fraction and the first fraction is I multiplied by x squared minus 1 over x squared minus 1. The second fraction there, the only difference is I multiplied by x squared plus 1 over x squared plus 1. But now we have a common denominator, and we will be able to combine these fractions. I'm going to simplify a bit. 2x multiplied by x squared minus 1. Distributing that, it's 2x cubed minus 2x. Let's do a little simplifying here as well. 2x times x squared plus 1 is 2x cubed plus 2x. Now that I have a common denominator, I can combine, but don't forget this minus in the middle gets distributed all the way through, not just to the first term. So this is minus 2x cubed minus 2x. So let's think about that. 2x cubed minus 2x minus 2x cubed minus 2x. So the 2x cubed minus 2x cubed, that's gone. And negative 2x minus 2x will be negative 4x over that common denominator. I'm going to bring down what we did here, and now I need to multiply these together. Multiplying fractions, numerators times numerators, denominators times denominators, that's true, but we just have, so we have negative 4 times x squared plus 1 to the 3rd. We have 3 times x squared minus 1 times x squared plus 1 times x squared minus 1 to the 1/3. When you are simplifying fractions, right, we have everything multiplying in numerators and denominators. If we have like bases, then we can simplify. So see all those like bases? I'm going to be able to simplify x squared plus 1 to the 1/3 and x squared plus 1. Let's just think of something that's a little easier first. What if I had 5 to the 5th power in the numerator, and in the denominator 5 to the 2nd power? Well, if you had 5 to the 5th over 5 to the 2nd, you would subtract exponents and have 5 to the 3rd in the numerator. It's very similar here. X squared plus 1 is to the 1st power. X squared plus 1 is to the power of 1/3. The exponent 1 compared to 1/3, 1 is bigger. So I have like bases, I'm going to subtract exponents, but when I take 1 minus 1/3, that's like 3 over 3 minus 1/3. I get 2/3. And there's more of those x squareds plus 1s in the denominator, so that's where they land. Now in the denominator, when I multiply x squared minus 1 times x squared minus 1 to the third, we have like bases and we're multiplying, so this time we will add exponents. So the exponent on x squared minus 1 here is 1, and we have 1/3. So 1 plus 1/3 is 4/3. Okay, so like bases, those pink ones were alike. So 1 plus 1/3 gave me 4/3. And then we're dividing here. And so we have like bases, x squared plus 1. So we have to subtract exponents. 1 minus 1/3 is 2/3. And we finally have our simplified answer that would match the back of the book. Oh, Bob, we just love your answers and we like to match you. Just for your convenience, here are several of the log properties that you might use once you take the natural log of both sides and want to start pulling things apart. Logs are very powerful in calculus. The ability to pull things apart to make the calculus so much easier is exactly why I love logs, and I hope you do too.